Hello and welcome everyone. My name is Sufyan Shafiq and today I will be presenting my findings on accelerated testing of camera dust mitigation methods. Working closely with the System Health Lab, my supervisors are Professor Melinda Hodkiewicz from the School of Mechanical Engineering, as well as Quentin Thomas of Warehawk. Camera systems and computer vision provide great opportunities for continuous monitoring of processes. An example many of us are familiar with is autonomous vehicles, which in part use computer vision cameras to detect objects on the road. Such systems can easily be disabled by obstructions like dirt on the windscreen, or the image quality can be compromised by dust deposition over time. So tackling this issue is critical if we were to rely on these systems at all. For this project, the SHL has been working with one such system from Warehawk that utilizes computer vision to monitor conveyor belts. By doing so, they intend to improve safety with better failure detection as well as save millions of dollars in unplanned maintenance cost. However, as shown in the diagram, the viewing window undersurface is susceptible to dust settlement, especially in a dusty mine site environment. It is no secret that the dust levels in the Pilbara mine sites here in Western Australia has been increasingly scrutinized recently, so it's crucial that this system is addressed to ensure the reliability of the system. With Warehawk as the case study, the research question was formulated as follows. How can dust settlement on an undersurface be mitigated such that visibility through the viewing window is best preserved? When formulating this research question, it was found through literature that there was an overwhelming focus on oversurface dust mitigation, specifically for photovoltaic applications. The findings from these may not directly apply to undersurface dust deposition experienced by Warehawk system. So yeah, that's part of the reasons why this research question was formulated as such. There was also a gap in accelerated testing that links dust deposition to acuity of computer vision. Most studies looked into dust deposition in terms of how much light the dust blocks, whereas we are more interested in the computer's ability to identify objects in the image. There's also an opportunity to conduct direct comparisons between different approaches to dust mitigation and study the interactions. To answer this question, the two main tasks undertaken were to develop the accelerated testing methodology and equipment, as well as develop dust mitigation solutions that combine different approaches. The method used in this project is as follows. The units to be tested are put in a dust chamber and the dust is agitated for 12 hours. The cameras capture the target image before and after the dusting. The target image is enclosed in a box that protects the image from dust contamination. This box opens up during image capture. The whole chamber blocks out all external sources of light to allow the light box itself to serve as consistent illumination for the target image, the importance of which will be explained in later slides. The target image is adapted from ISO 12233 that measures camera lens performance. So this custom image here can be used to measure the transmissivity of the viewing window via the white spaces, contrast resolution via the contrast gradients, and spatial resolution via the shrinking bars. Transmissivity drop is the common metric used in literature to measure dust settlement. This is especially relevant in the photovoltaic space where a change in transmissivity directly relates to a change in power generated. Contrast resolution is chosen as it pertains to computer vision in general, where algorithms use it to discern objects information from an image. Spatial resolution is chosen as it's specifically important for Warehawk's application where conveyor belt thickness is similarly measured. I'll go a little bit into the performance characterization for transmissivity. It is measured by taking the mean grayscale value of the white space from the target image and seeing how it changes after being subjected to dust deposition. So the lower the transmissivity drop, the better the performance of the dust mitigation solution. Contrast resolution measures how well the camera system measures a step change in grayscale value of the target image. For example, the source image here steps the grayscale value by 3 points at each interval, and then it does it 50 times over the whole strip. A perfect camera system would report a 3-point interval as well. What we are measuring, however, is how this interval changes after being subjected to dust deposition. The lower the contrast resolution drop, the better the performance. Spatial resolution measures the smallest feature in an image that can accurately be discerned by the camera system. This is done by applying a canny filter, as you can see there. It's used for edge detection. So the thickness of the smallest full unmerged line represents the spatial resolution. As you can see, as the lines get smaller and smaller, the the canny filter algorithm can no longer detect the edges and just merges them into one bigger block. So the smallest full unmerged line represents the spatial resolution of the system. So the smaller the spatial resolution increase after being subjected to dust deposition, the better the performance. Through literature review, it was determined that there are 3 dust mitigation approaches worth pursuing for Wet Hawk's case. They are hydrophobic coating that is applied on the viewing window, ultrasonic vibration via piezoelectric actuation, a lens hood that blocks dust flow path, as well as a positive pressure filtered airflow added along with the lens hood. The experiment was designed as a full factorial experiment which tests all possible combination of the 3 factors. This is what allows us to not only identify the contributions of the individual factors, but to study the interactions between them as well. This is the test setup. The dust chamber is a repurposed sandblaster. Those tarps are there to block light, as mentioned. Inside is the light box that houses the target images. It is servo actuated and LED lit. Also inside, hanging from the top, are the cameras. You can see the 3 airflow tubes that are not in use in this particular instance. The cameras hang from a lid that also houses the blower and filter, as well as the control box that runs the experiments and controls the whole setup. The sandblaster is connected to a pressure line, and the dust agitation is controlled via an air regulator and a solenoid valve. Here's an example of before and after a test for the control experiment where no solution is applied. On the camera viewing window, dust deposition is clearly visible. Like it's clearly different before and after. As far as the captured images are concerned, there's not much difference that the eye can see. The after image is slightly darker and a bit more grainy, but that's about it. So let's hope we can see a clearer picture once we look at the data. Here we can see the effect of each factor on the transmissivity drop. As mentioned before, the lower transmissivity drop, the better the dust mitigation performance. For context, the control test, as you can see there, candidate ID1 saw a transmissivity drop of 0.15. Combining all the mitigation approaches, candidate ID12 netted a transmissivity drop of only 0.015, which is a whole order of magnitude lower. We can see that on average, the lens hood with airflow performs substantially better than other methods, able to reduce transmissivity drop by 0.082, with the worst performing being ultrasonic vibration, achieving a transmissivity drop of 0.027. We can extract more information from this data by looking at the test pairs. The test pairs are only differentiated by the factor identified in the x-axis. We can see that none of the test pairs have positive slope or cross over each other. What this means is that there are no negative interaction between factors. It also means that turning each factor on always contributes, however small, towards reducing the transmissivity drop. As far as interactions go, the strongest interaction is between hydrophobic coating and ultrasonic vibration. As can be seen here, without hydrophobic coating, turning on vibration makes minimal difference to the transmissivity drop. However, with hydrophobic coating, we see massive benefits from turning on ultrasonic vibration. What is even more interesting is if we look at the test pairs, we see that comparable performance can be achieved without the use of airflow if we use both hydrophobic coating and ultrasonic vibration together. This is especially relevant since airflow is the most cumbersome method in terms of filter maintenance. It also takes up a considerable amount of space to have a blower and filter on the system. Looking at this, it might not be the best trade-off for the small benefit that you get. As far as contrast resolution and spatial resolution is concerned, dust deposition to the level where experiments got to didn't seem to affect these performance metrics much at all. The drop in contrast resolution was so small that some even went negative. As well, there's no discernible change in spatial resolution as a result of dust deposition, except for the control test. Obviously, what you get from this is that the target images weren't not adequate for the specific system that we were testing. So future tests would require having some initial information so that we can curate the target image to fit the systems that we are testing. We didn't know how to do this before, but now, armed with this information, we have a clearer picture of how to do it. Now, into some discussion. From literature, it was identified that dust concentration in the air as well as humidity were important factors that affect the rate of dust deposition. During the experiments, these factors were kept as covariates, meaning they were not controlled. Additional testing will allow us to see if the effects of these parameters are significant, but at the moment, we have yet to conduct any repeat tests because that ended up being out of scope for this project. The individual approaches can be further refined. This may have different effects on different approaches and it may lead to different conclusions. For example, it is possible that we may see massive benefits from tuning the ultrasonic vibration specifically to our system. Another thing is the viewing window was washed after every test instead of being changed out. Although much care was given to this process, this could have had lasting effects like micro scratches on the window that progressed as we moved from one test to another. From the results, we were unable to obtain a great amount of information with regards to contrast and spatial resolution. As mentioned, this can be rectified in part by refining the target image. Instead of having bars ranging from 2 millimeters all the way to 1 pixel width, we should curate the image to what we expect the effect will be. We did not have this information at the start. We didn't know how much the contrast and spatial resolution will be affected by dust. But now that we have a better understanding, this can be improved. Lastly, a full experiment lasts 3 weeks. This does not allow for repeat tests since the bulk of the time was invested into developing the method, equipment, and solution combinations. But now that we have all that sorted, this can be used in the future for this or other dust environment projects. Although we gauged the test cycle time of 12 hours from an initial test that saw the dust deposition starting to plateau after 1 hour, we still need to run the test for a longer period of, say, maybe a week to ensure that 12 hours is actually sufficient. It just wasn't feasible given the time frame of this project. Also, as mentioned, it is recommended that we work towards a solution to control the humidity and dust concentration, both to have a more field applicable test as well as increase the confidence in the results. This methodology also still requires validation from results of camera systems from the field. This will also lead to calibration where we can, for example, say 12 hours in the chamber translates to maybe 3 months in the field, etc. Obviously, the equipment can further be refined. Ceilings, especially, were a problem in my experience. We naively assume that an out of service sandblaster can serve as a dust chamber, but not exactly. There were leaks everywhere that were dealt with using temporary solutions. Also, environment sensors can be improved on the equipment, and the test image, as mentioned before, can be improved. Finally, further down the line, it's possible that we end up producing a solution matrix to recommend the different solution combinations specifically for different applications, depending on the humidity, temperature, use of space, etc. Thank you for listening.